All right.
All right, everybody. It is that time of the night.
Can you hear us in the back all right?
Volume sounds okay. We didn't do a sound check.
All right. Thank you.
Apologies to those near the speaker. We're going to try not to blow your ears out. What's up, everybody? We are doing it. Brian and Adam run the AV, and they're doing bigger and better things over at the downtown campus at UTSA. So we're on a skeleton crew, and boy, oh boy, give those AV technicians some love, seriously, because they do a whole lot for everybody. But yeah, what's up? This is Astronomy on Tap. My name's Aaron. Mike over here on my right.
Hello.
Erica further right. Jasmine doing Astro News later in the crowd. Brian and Adam, like I said, are usually here, but they're over at the downtown campus. They're like teaching something. It's something to do with small business and Linux. And then Caleb is writing his dissertation, so he's doing that. And then Thomas is online. Sam is taking a finance class.
Yeah.
Sam's doing same things, I guess.
Getting that money.
How many first timers to the event tonight? No one? Oh, okay. I got a couple. Cool. Glad you're here.
Welcome.
And I'm guessing everyone else been here, done that, been around the block a couple times, seen AOT. You know our faces by now. Mm-hmm. Yeah, not got. Yeah.
Well, I have the logos ready now, so that's one hurdle down.
Shirts, as they have been the entire year, are in progress. My personal goal is by December, don't hold me to it.
Hold me to it.
Yeah, hold Michael to it. Yeah, I did a whole other intro.
Okay.
But for the first timers here tonight, Michael, what is Astronomy on Tap?
Yes, I will explain that, but I want to give a caveat for our people online and for anybody that watches recordings. We have the audio and the PowerPoint going on. If you're wondering why we don't have the camera, even though it's up there, we couldn't get it to work. The camera's not working tonight, unfortunately. So I'm recording it on my laptop, and then we'll splice them together after post-production, and hopefully, if you want to watch the recording, we'll have the audio recording of this, and then the camera recording that is ongoing right there. So, for you, sorry, online people, but we still love you. So, what is this all about? Well, it's a worldwide phenomenon. It started over 10 years ago in Brooklyn, New York, and now there's locations all across the globe, including our. Sorry, Sam added that on me. And there we are, the yellow dot, right there in San Antonio. And what separates us from the rest, right? There's a whole bunch. Why are we special? Well, we are interesting. We have two great speakers tonight, and they're going to give some great talks. We're interactive. You'll be able to ask our speakers questions via the text line, which Aaron will share in a little bit. And a chance to win prizes at the end. We do trivia at the end of every day, and that's always the fun part. We want everybody to have fun and enjoy tonight, so that's what it's all about. And that's right, we got rid of the socials. We have information for how you all can follow us and keep along with us, which will come later, but especially if you're a first time, come find us afterward if you'd like to be a second time or a third time. So, keeping with our tradition of putting a user-inputted photo, once again, Lee, there you are. He's got some great photos. This is Lee's photo of Milky Way at Big Bend, which, having been to Big Bend a few months ago, it does look like this. Can confirm.
Can confirm.
So, yeah, if anybody takes a beautiful picture, a beautiful dark sky picture, and you want us to feature it, just send it right over to Sam. There's an email later in the slide, but go out and explore. Go out and see the dark night. You don't have to drive too far to get views like this in Texas. All right, Aaron, what's our schedule?
Tonight's schedule. First up, we're going to have Danielle Bovie UTSA PhD candidate, talking about characterizing massive, in all caps, planets with direct imaging and precision astrometry. Then we're going to have a break and UTSA Astronomy's Club, which is it's just Jasmine now. It's Jasmine's going to give us all the updates of everything astronomy. And then we're going to have Patrice Smith, another UTSA PhD candidate, talking about observing the moon from backyard to spacecraft. And then after that, we're going to have our space-themed trivia that Sam always likes to throw a curveball in, so we'll see what that one is tonight. And next slide. So usually we have the number up here. However, we got all 3 laptops running at once doing something else. So this is going to be the number tonight to text questions to. If you want to send a quick text to that number, go ahead. So you got it in your phone ready to go. It's going to come up later at the end of the talk. But I recommend, and I'm stalling so everyone can like write it down, memorize it, put it in your phone or something to text questions during the talk. So that way afterwards we have some questions for all the speakers. And with that, I'll let Erica introduce our first speaker of the night.
Now it is. All right. So there is this one. Okay. So while we are getting her set up, it is my pleasure to introduce Danielle Bovie, who is a third-year PhD candidate now in physics at UTSA. She got her bachelor's in physics and astronomy from the University of Rochester in upstate New York in 2021, and she stayed at Rochester for her master's in material science, which she completed in 2023. She now works with Thang Curie on the direct imaging of exoplanets. So, Danielle, what is your drinking word? Oh yes, for the couple of people who are new, we have a lovely tradition where when our speaker says their drinking word, we shout a big whoop! And then they will continue. Cool? Well, hopefully y'all can hear me, but without further ado, Danielle. What's the word?
So the drinking words, rather than word, is direct imaging. All right, well, thank you for the introduction, Erica. So the planets that I look at are exoplanets, which are planets around other stars. So in our solar system, there are 8 planets that orbit around our star, the sun. But we now believe that all of the stars that you see out in the night sky likely also have planets orbiting around them. So as of right now, there are around 6,000 confirmed exoplanets, but all of this is relatively recent. So the first exoplanets were detected in 1992 around a pulsar, which is a type of neutron star which forms after a massive star dies. But because these planets were orbiting around a dead star, many people didn't trust these detections. So at this point, people still did not quite believe that exoplanets existed. But the first exoplanet around a sun-like star, so a star during the main sequence of its life, was first discovered in 1995. So this was 51 Pegasi b. And I got the opportunity to visit the observatory in France where these detections were made. So this photo right here, down on the bottom right, is an image I took of the instrument that was used to make these detections. And as of now, it is in a display case. All right, so there are many ways to detect exoplanets. But with most of them, you're not seeing the actual planet. You are, sorry, my formatting got a little bit messed up there, but regardless, with most of the detection methods, you are only seeing, you're only inferring that the planet exists, not actually seeing it. So with 51 Pegasi b, it was detected using the radial velocity method, which velocity is sort of crossed out there, but with the radial velocity method, the massive planet is able to exert a pull on its star and causes the star to wobble. And what you see is the Doppler shift, so the shifting of the star's spectra as the star moves closer or further away from the viewer. The most prolific of the detection methods is the transit method. So when the planet crosses in front of its star, it blocks out some of the star's light, and the star slightly dims. And one of the strangest detection methods is probably microlensing. So with microlensing, the gravity of a massive object, such as a star, is able to bend the light from a source behind it. So that bending actually acts like a lens, and the source is magnified by our star. So if this star has a massive enough planet around it, the planet can also slightly bend the light and also have a slight magnifying effect on the source. So you'll get a large amount of magnification from the star and a smaller amount of magnification from the planet. Then there is astrometry and direct imaging. So these are the two detection methods that I use. So they're going to get their own slide, and I'll talk about them more later. But there are many other sort of weird detection methods that I'm not going to get into. But one example is pulsar timing. So the very first exoplanets that were discovered in 1992 that I mentioned on the previous slide were detected using pulsar timing. All right, so I will start with astrometry. So astrometry is similar to the radial velocity method. With both methods, the planet's mass exerts a pull on its star, causing the star to wobble. With the radial velocity method, as I mentioned on the previous slide, you're looking for the shifting of the star's spectra, so the Doppler shift. But with astrometry, you're looking for the actual movement of the star compared to its surroundings. So this is astrometric acceleration that is not consistent with the movement of the galaxy. So you have your star, which moves with the galaxy, but if it has a massive planet, it will wobble. So it kind of like spirals as it moves through the galaxy. All right, so direct imaging, or high contrast imaging, is the only detection method where you are actually taking an image of the planet rather than just inferring its presence. So the high contrast is referring to the high contrast between the very bright star and the dim planet. So over here on the right, I have an example of an image of an exoplanet. So on my very first slide, my exoplanet slide, I included a fun artist depiction of some of the detected exoplanets. However, that is definitely not what we're able to see. So what we actually see, so the planet itself is that cluster of pixels that I have circled there. And as I mentioned, the star is very, very bright. So just like on a very bright day where you might hold up your hand to block out the light from the sun in order to see something else that's in the sky, we use a coronagraph to block out the light from the star in order to be able to see the planet. So this is why we have a sort of cartoon star marking the position of the star, because again, we're blocking out the star's light. So of the 6,000 exoplanets that have been discovered so far, 25 have been detected with direct imaging. All right, so unlike most detection methods, we are detecting photons from the actual planet's atmosphere. So this makes it great for atmospheric characterization. So with our current technology, we're able to detect massive Jovian planets at wide separations from their star. So let me try this out. This sort of red boxed region up here in the figure. We are also able to detect low-mass brown dwarfs, which are intermediate between planets and stars. And we can use these as analogs for massive planets. So with the upcoming extremely large telescopes, which are their real names, I swear, and NASA's Nancy Grace Roman telescope, we will be able to image planets that are much more similar to those in our own solar system. So down here rather than just up here. And eventually, someday, with direct imaging, We will someday be able to characterize the atmospheres of Earth-like planets with NASA's planned Habitable World Observatory. All right, so all of this is great, but why do we also need astrometry? So massive planets with wide orbits will exert a noticeable astrometric acceleration on their star. As I said, the star will wobble. We can identify young accelerating stars and follow them up with direct imaging. So astrometry increases our chances of detecting a planet and also allows us to constrain the planet's mass and its orbit. And with direct imaging, that one was a little bit stronger, we will then be able to detect the planet and characterize its atmosphere. So OASIS is the intensive survey that is being led by my advisor, Thayan Curry. With the survey, we have 42 nights on the ground-based Subaru and Keck telescopes, with most of those nights being on Subaru. Subaru is so important that it is the background image for my slides, so you can sort of see it there peeking behind my text and images. So we will be targeting over 100 nearby young stars with astrometric accelerations from the Hipparcos Gaia catalog of accelerations. And so these are stars with accelerations that suggest they might have an unseen massive planet. The astrometry improves our chances of discovering a planet and allows us to better constrain the mass. We use Skexio, which is Subaru's extreme adaptive optics system, and CARIS, its integral field spectrograph. And so those two instruments are shown here in the image on the right. All right, so for the survey for initial discovery of the planets, we use the low resolution, which is a resolution of about 20, JHK broadband mode. But for my work, we revisit these new discoveries with a higher resolution, individual J, H, and K bands with a resolution of about 70. So we do this in order to further characterize the planets, and we complement this data with thermal infrared from NERC-2 on Keck. And this allows us to characterize the planet's atmospheres in greater detail. And with both my new data and the previous data, this gives us a much longer baseline. So this improves our constraints on the planet's orbit and its mass. So I have been focused on the planet HIP 99770b, a very catchy name. This planet was discovered during the pilot phase of the survey and was published by my advisor in 2023. We then revisited the planet in the higher resolution in June and July of 2023. So throughout the rest of this talk, I'll be talking about this work. But if you are interested, my paper is about to be published on this in the Astronomical Journal. Thank you. So if you're interested, it is on arXiv, and I've included the QR code here that will take you to that link. But yeah, so my high resolution images are up here on the top. So the H band is on the left, and the K band is on the right. And once again, the actual planet is that circled cluster of pixels. And below that, I have my spectra. So the H band is in red, the K band is in orange, and this is plotted over top of the spectra from the initial discovery, which is in black. All right, so next I fit the orbit using Orvara, which is a Markov chain Monte Carlo dynamical code. And we modeled both the host star's astrometry from Hipparcos and Gaia, along with the planet's relative astrometry from direct imaging. This allowed us to constrain orbital parameters such as the mass and the semi-major axis. So for the mass, we found 15 Jupiter masses, and for the semi-major axis, roughly 16 AU. And with both of these, we were able to improve the precision about 20% from the initial discovery. So to characterize the planet's atmosphere, I first compared my spectra to the over 300 objects in the Montreal Spectral Library. So that's up here on the top left. So the best fitting, the closest matches to my spectra is down here in this region at the bottom. And of those, the absolute best fitting was a brown dwarf, which I'm showing on the top right. So from this, we found that my planet most likely has a spectral type of L6 to L9.5, which corresponds to a temperature of 1300 to 1500 Kelvin. Next, we also compared the spectra to other well-known exoplanets and brown dwarfs. So that's what I'm showing down here on the bottom. From this, we found that my planet has an atmosphere that is sort of intermediate between younger planets and older brown dwarfs. So to continue our atmospheric characterization, we also compared to models. So I used 4 different atmospheric models, which are shown up here in the figure. Of them, the best fitting was the one that's shown in blue, which is Sonora Diamondback. So all of these models vary the planet's temperature, gravity, chemistry, and clouds. And so we're able to put constraints on our planet. So all of the models broadly agree on a temperature in the range of 1300 to 1400 Kelvin, which is consistent with what we found by comparing to real objects. We also found a slight preference for higher gravity. So the Nancy Grace Roman Telescope's coronagraphic instrument, or CGI, is planned to launch in 2027. So the main goal of CGI is a technology demonstration on testing out the use of adaptive optics in space. So this is an important step for NASA on the way to the Habitable Worlds Observatory. So I evaluated HIP 99770B's potential as a CGI target. I first used Orvara dynamical modeling in order to plot the predicted position of the planet in January 2028. So that's that image up there on the top. So based on its position, it will be well within the CGI dark hole, which is the region that is sensitive to being able to detect the planet. So that was good. So we moved on to modeling the expected contrast. So basically how bright the planet is in comparison to its star. And we did this for the 3 different CGI passbands. So those are these ranges right here. And what we found was that at 575 nanometers, so this first range here, it is much too faint. So there's sodium absorption there, so that's why it sort of dips down here. But the other 2 passbands, so 730 and 825 nanometers, seem to be bright enough and means that this planet should be a good science target for Roman CGI. All right, so as I mentioned, I have pretty much wrapped up this work and my paper will be out soon. So what is coming next? Well, I am planning on continuing my high-resolution follow-up of some of our recently discovered planets and brown dwarfs, including these 2 that I'm showing over here. And after I've completed a number of high-resolution follow-ups, I can combine all of this high-resolution data together to determine how massive planets' luminosity and mass evolve with time. And then hopefully we will also be able to follow up on some of these targets using Roman CGI. All right, well, thank you.
Can't tell.
Do you want to use this one?
Wait, if I put it, yeah.
Here, we can trade off.
Thank you, Danielle. That was a great talk. So, do astronomers pick a detection method for their career, or do they use what's available whenever they can?
Yeah, so there are definitely people that will focus on one particular detection method, but honestly, mostly it is whatever is available. And as I mentioned, I use multiple detection methods, but we are also starting to include RV data as well. So yeah, people definitely switch between methods depending on like what exactly they're looking for.
How far away are these planets that you study, and then any other exoplanets that we found?
I mean, I don't know the distance in anything that would be meaningful to most people, but like the planet that I've been talking about is 40 parsecs away, if you know what that means.
And Michael's holding the slightly robotic-y. Or we can switch.
No.
40 parsecs, that's like, what, 120 light years? So far.
Far, yeah. Far,
Just-
but in terms of the galaxy,
Yeah.
close.
Is microlensing responsible for why the sun and moon look larger on the horizon?
So no, that would not be microlensing. That has to do, I mean, it is like a similar like bending of the light as it comes through the atmosphere, but that's not due to gravity.
Yeah, it's like an illusion of like, yeah, it's a perspective thing. You can see big things around a big thing, and so it looks bigger. Will they let you see the telescope if you own a Subaru?
So actually, if you can make your way to Hawaii and make your way up to Mauna Kea, you can actually just go up to the Subaru telescope. You can't go inside, but anyone is allowed to just like go up there and walk around the telescopes.
So why would you want to use different wavelength bands, like the H and the Ks? What does each wavelength band give you?
Yeah, so basically the different wavelength bands are translucent at different parts of the atmosphere. And so more of the spectra that we can cover, the more information we have. So like one of the things that's really helpful, like especially with characterizing the atmosphere, is certain elements will absorb at different wavelengths. So like I mentioned the sodium absorption where it dipped down. So at that particular wavelength, the atmosphere absorbs sodium. But at other wavelengths, it doesn't do that. So the more of the spectra we can cover, the more we're able to tell what the atmosphere is made up of.
And what are all the little splashes of light in the images that aren't planets? How do you tell the difference between those blotches and the planets themselves?
Yeah, that's an excellent question. So there's a lot that we have to do. So as I mentioned, we use a coronagraph to block out the light from the star, but still some light leaks from around the star because we don't want a like infinitely big coronagraph, otherwise we won't be able to see our planet. So we have different subtraction methods to try and reduce the amount of light that we see, but unfortunately that also introduces little artifacts. And those artifacts are those blobs that you can see. And so in most of my images, none of them looks particularly like a planet, but they can look very similar to planets. So a lot of what we do is trying to make sure that the blob that we are seeing is actually a planet and not just an artifact from our subtracting off the star.
And final question, what is adaptive optics? And spoiler for the ones who know, why would you need it in space?
Yeah, that's an excellent question. So with adaptive optics, so we'll get to the second part of the question eventually. But first, it is most important on the ground. So on the ground, what we're dealing with is you're looking through the atmosphere. And the atmosphere is very turbulent. And it causes the light to sort of like wiggle around, and it distorts any image that we're trying to take. So adaptive optics is super useful because what we do is basically we can figure out how much the atmosphere is being distorted, and then we can correct for it. So we use deformable mirrors. So it's basically a mirror that can kind of like move around to match the shape of how the atmosphere is distorting the light. And so then we get a clear image. And so that's why the second question is particularly interesting. So if we use adaptive optics to correct for the distortions caused by the atmosphere, why would we need it in space? Because there is no atmosphere. Well, so on Earth, adaptive optics is working really, really quickly in order to correct for atmospheric distortion. But in space, you can use it on a much slower scale, and you can actually use it to correct for distortions that are caused by your optical setup. So with adaptive optics and with any sort of instrument setup, you're going to have tons of lenses and mirrors, and these are going to cause distortions. But you can use adaptive optics to correct for those like inherent distortions in your telescope.
Great. Thank you, Danielle. Let's thank our speaker one more time. Awkward. I forgot to hit the next slide. But a lot of you got it. Here's the number again. I'll show it again here in a minute. Why are you up here?
I just thought of something because we were talking about the shirts, and we've been talking about the shirts for a while. And I know I've got a job to do, but genuine question, because this will help me. How many of you, the minute we get the shirts, or maybe a month later, would buy a shirt? Raise your hand right now.
At least 5.
All right, that's about half the room. All right, thank you.
Yeah. Everybody wants a shirt, and especially with the new logos we got that Sam still hasn't put in the new slides. Yeah. All right. Lindsay, question for the room? Good question. Huh? Yeah, it's in our... Maybe during the break, I'll put it up in the slides. I think I'll do that, and then everyone can see the new logos. They're pretty slick. Yeah. Yeah, if anybody wants a small of the old t-shirt, we have 2. But we're going to take a quick break, say 7:40. We'll come back at 7:40. Here's that email if you have a nice image you would like to use as our background for our monthly AOT installment. See you at 7:40. All right, everybody. It is that time of the evening once again. Thank you, Lindsay, for the inspiration. Some of you may have seen these before, but if you haven't seen them, especially for everybody new in the room, hear ye, I have new content for you. Find a close to your conversations, find a hand for your beer. New logos. Shirt. The spaceman. Yeah, the shirt. We're thinking the shirt's going to be the colorful neon spaceman helmet, SAT skyline. And then this one, I just like the cool like talk show theme of that one. We're going to put on like mugs and stuff because it's a good negative. Yeah, those are the new logos, and I reminded Sam to put them in the slides, so we'll see if that happens. Up next, we have Astronomy in the News, presented by Jasmine Singh. Everybody get up for Jasmine Singh.
Hold on. I always do it backwards. All right. Hi, everyone. Happy October. Happy spooky month. Yeah, so we're going to just get into the Astro News. Today, I have the headline about new astronauts dropped, because they did. You may have heard about that, but we're going to talk more about that in the slides. So let's get into it. All right, I am not Caleb, so I am not good at this. As you can see, there is not a pretty image up here with everything on it, and I'm sorry, I will get better at that over time once I learn how to do it. So right now, we just have a generic image. I'm really sorry about that, but if you care a lot about what the sky looks like, go look it up. But I do have the highlights, so I got something. So the Orionid meteor shower, it's going to peak around October 21st or the 22nd, and you can see up to 20 meteors per hour before dawn, so I think that would be really cool. So try to go out and see that at the end of this month. In terms of planets, Saturn's actually going to be the most visible of the planets. And this weekend, it's going to appear right next to the moon, which it'll be like a nearly full moon, but you should still be able to see a little dot next to it, so go check that out too. It'll look cooler through like a telescope or something, so if you have access to a telescope or binoculars, go see that. And then Jupiter is going to rise after midnight, and it'll be pretty bright until about dawn, so see that. And then in terms of objects, the most important object would be the Andromeda Galaxy this month. It's going to be at its highest and brightest this month. And it looks like this through binoculars. All right. So Danielle actually gave a good segue on this because she mentioned it briefly in her presentation. We have officially discovered 6,000 exoplanets, which I think is awesome. Yeah. So, as Danielle also mentioned, the first exoplanets were confirmed in around the early 1990s, and since then, the discoveries have only accelerated incredibly fast, especially after missions like Kepler and TESS, which has led to 6,000 and counting. And this exponential growth is going to help us narrow our search for potentially habitable worlds, and I think hopefully in the future with new telescopes and new missions, we can get that number to 10,000 and higher. So I'm really excited that we got 6,000 worlds. We also don't have like a confirmed this was the 6,000th planet. We just kind of discovered them and go. So there's no confirmed 6,000th planet, but yeah, the number has reached 6,000. So that's really exciting. Oh, as mentioned before, the 2025 astronaut candidate class has been announced, if you haven't seen in the news. And so NASA has introduced 10 new astronaut candidates chosen from more than 8,000 applicants, some of which I am friends with, which is crazy that I have friends that were able to apply to be astronauts. And, even if you don't get selected, I feel like the honor of applying and meeting all those requirements is cool in and of itself. So, it's cool to have that rejection letter, I think. And I don't know, it'd be an honor. So I don't know if you're paying close attention to this picture, but this class in particular is very special because for the first time in history of NASA astronaut classes, the women outnumber the men in the class. We have 6 women and 4 men out of the 10 astronauts. So I don't know, that's really huge. I think as a woman myself, that's great for the future. That's great for, little girls who want to be astronauts one day and can see themselves in something like this. So, we're just proving that this is becoming more and more possible each day. Okay, now this one, last but not least. Perseverance discovered potential biosignature on Mars, which I know sounds crazy, but let me clarify real quick. So last year, you may have seen in the news, there was a very special rock that was found on Mars, and Perseverance drilled into a rock called the Chayava Falls, and it extracted a sample. And so since that time, over a year has passed, scientists have been doing analysis on it, and they finally announced that the sample contains a potential, emphasis on potential, biosignature. So I think there have been a lot of headlines that kind of exaggerate things so that they can get clicks, but it is not confirmed that this is a sign of life. It is not confirmed that this has anything to do with life. Similar features could be produced by abiotic chemical processes. We need further analysis to figure that out. But I think that this is a huge step in terms of finding life or anything related to it, especially with Mars. So, contact your Congress people whenever. We're shut down right now, but whenever you can, contact them because we need money. Yeah, they're still Oh, they are? I don't know. I don't know about the government. Well, contact them because we need money so that we can bring the Mars samples back and do further analysis and put money into this. All right, last but not least, we have some new images. So we have Sagittarius B2 from James Webb. We have this little thing that's in the, I never know how to say it. How do you say it? Yep. In there. And then this one I found was pretty cool. This is the recent hurricane. This was from a few days ago. Hurricane Umberto from the ISS. So I think that's pretty cool. Yeah, go, as always, go online and look at these images in more detail because they're really cool and you can kind of zoom in forever and ever. So yeah, that's it for the news and the images. We have some events to talk about, a lot of which are happening this week. So South Llano River State Park observing, the date has not been confirmed, but they are looking at the 18th or the 25th for that, so it's tentative right now. Observatory night is this Friday at UTSA. I think they start at 8, so yeah. It's something like that, 8 o'clock. And then the San Antonio Astronomical Association, or SAW, they meet every Wednesday at sunset at Raymond Rimkus Park. And we have observed the moon night, which will be at Guadalupe River State Park on the 4th. And they also have First Fridays at Scobie, so this Friday they'll have an event there. And then at Scobie on October 3rd, so Friday, we will have International Observe the Moon Night where AOT will be there, GSPS will be there, UTSA will be there. We'll have all our little tables, so come out and see us. And they also have shows every Friday except Halloween. So go out. Thank you.
Thank you. All right, thank you, Jasmine. Good segue here because International Observe the Moon Night, our next talk with Patrice Smith, is all about. Oh, reminder to text your questions to this number. So if you want to type it in now, just in case you want to text on the fly, there you go. All right, Patrice Smith. Yes, International Observe the Moon Night. Come visit us on Friday. We'll be out on the Scobie, AOT, UTSA, GSPS, SWIRI, all of us. And Patrice here will talk about the moon. So a little bit about Patrice. Patrice was born and raised in California. She completed her undergraduate studies at the University of Hawaii at Hilo, with a Bachelor's of Science in Astronomy and in the concentration of Physics. Her undergraduate research included work on identifying near-Earth members of the Euphrosyne asteroid family, as well as mapping out hydration on the lunar surface. She spent 2 years at the telescope operator for the James Clerk Maxwell Telescope before arriving at UTSA. Now, in the UTSA SWIRI Joint Space Physics Program, she works on constraining the composition and variability of the lunar exosphere. So without further ado, here's Patrice, whose drinking word will be...
International. All right, so I'll be talking about my research, but in honor of International Observe the Moon Night this weekend, there we go. I'll also be going over how we can observe just normally in our backyard, and I'll kind of work our way out to all the way through observing with spacecraft. So just really quick, we'll talk about International Observe the Moon Night as a whole. And we'll go over what backyard, quote unquote, observing is, as well as what kind of ground-based telescope observations of the moon we've had. We learned a little bit earlier about ground-based telescope observations as a whole. And then we're going to talk a little bit about this topic called lunar hydration and exactly what kind of research field that is and was. Then we'll go over some lunar orbiter observations and go into the moon's exosphere after. So, as advertised, the Scopie Planetarium and Challenger Center will have an international Observe the Moon Night event. Many of the people who are running AOT will be there, and so as you guys usually show up on a monthly basis, it sounds like it'll be a good turnout on Friday from 6 to 10 p.m. Highly recommending just kind of going out and observing the moon, however that means to you. So we kind of put quotes around the word observing when it comes to International Observe the Moon Night. If it's ever cloudy, you have other resources to basically go and look at the moon in whatever form means the most to you. So for example, if you're like me and you have a device that you're usually very attached to, the Lunar Reconnaissance Orbiter camera system has its website that posts some of the most interesting photos of the moon. And so it's kind of qualifies under its little international Observe the Moon Night. So this image on the left, for example, comes from the wide-angle camera. It's a composite image of the entire near side of the moon. So any part of the moon that you go out tonight and you see, it's going to have a feature that's on here very clearly. So if you can see looking out into the sky, some dark spots, some light spots, some craters, you can always go to something like this to compare to and where it has a lot more resolution. It has other images like altitude profiles, so you can see things like craters much more clearly and their floors versus like their sides and the walls around them. But you can also see very modern pictures like this one on the right. So it's hard to see, but there's a little red dot right here towards the center of it. That is the original landing site, now crash site of one commercial lander. So we're kind of in this new era where we have all of these different companies sending all these landers out. Trying to land on the moon seems to be the key word. They were working real hard in the 60s because we have not been able to get that back down. So that is actually now the crash site of a previous landing attempt. So exciting things going on in our day and age. But in general, I like to think of backyard observing as just whenever you're out and you see the moon or anything else in the sky that you're kind of in awe of, it's a good time to stop and kind of take in the fresh air sort of thing. So for example, I was driving by the airport and saw the moon in the sky and I thought it was beautiful and I hadn't seen it that well in a long time. Pulled over, blocked off traffic by the post office airport kind of thing. You can actually see Southwest in the corner here. I shouldn't have pulled over where I did, but I got a good picture of the moon here above this beautiful tree, and instead of people crashing into me, other people pulled over to see what I was looking at, so I get to share that at least. So, so whatever observing means to you, unaided eye or binoculars or telescope, there's things that you can see either way. So in particular, to me, the very kind of left edge of the moon in our hemisphere is a little bit darker than the other side. And so that's what we call Maria, or seas. So this area right here is geologically very different to the lighter areas around it. So These are kind of flood lava plains from large impact features in the past. So we have things like Mare Imbrium, so that's that top circle here, resulted from one impact billions of years ago, melted the whole area around it. And you have other larger areas around it. So this is Oceanus Procerlium, I think is what it's called, where the impact lava zone was so large that it just kind of melted the entire side. And we don't really see that on the backside of the moon as much. Other things that you're likely to be able to see with the unaided eye are really bright craters. So this one in between the two, oh, there we go. The one in between the two large Mare areas, this one is Copernicus crater. So it's a much newer impactor. You can kind of see because it's over top the two floodplains. And this one in particular, Tycho or Tycho, is one of my favorites because aside from seeing how intense the impact is in its zone, you can kind of see how big the striations are. So this extends all the way across the moon. So you get a sense of how impactful the heavy bombardment period of that era was and how many things were just flying around, basically. So in particular, I like to look alongside wherever the Terminator is going to be on that day. So this is a very, very rough drawing that I did. But I basically wanted to make little dotted lines of where the Terminator should be. So tonight, we're at like 67% illumination. That's this pale dotted line here. And when you're looking along the Terminator, usually things have a higher contrast. So if you're like me and you don't have the greatest eyes, you can see things much more clearly. So in particular, tonight, I was trying to look for Copernicus crater, for example, because it pops a lot better. If you're going October 3rd out or just going to the Scopy Planetarium, you can also go and see the edge of this whole area, so you'll be able to see the Tycho striations a lot better on Friday. And then if you're going out for International Observe the Moon Night, this little edge right here is my roughest drawing, but you'll be able to see the majority of the moon, including a really enhanced part of Oceanus Procerlium, basically. So there's a lot of cool stuff to see just with our unaided eye, and it gets even better with binoculars and even better with a telescope. But we also have really cool events, nicely enough, with the moon. So for example, lunar eclipses are something that I always enjoy. We got to get this view during an international conference. Michael had one of the best photos of it, and you can see actually the reddening on the side of it there. So there's a lot to see just on its own, but also once you get to larger telescopes, that's when you can really do some really serious and large research, as we saw before. So going into ground-based telescope observations, we'll talk about them with the moon, but we saw before just how powerful they are with things like exoplanets, for example. These are really useful for long-term observations that you need to do really, really long studies for over the years. One example is the lunar hydration topic. So a couple of decades ago at this point, some spacecraft passing the moon calibrated on the moon and took observations of it, finding kind of really weird features that they weren't expecting. Previously, it was just kind of generally known that we had things like ice at the poles of the moon. But these spacecraft were basically, over time, reporting sites where they could see something like water or something like hydroxyl, basically. And we'll go over what that feature was exactly. So we've had 3 spacecraft that basically had papers that were saying, that's really interesting. Excuse me. One is the Cassini spacecraft, so that's the one that went to Saturn. So that was back in 1999, and in 2009, someone published a paper like, hey, we had this weird data, and we were not quite sure if anybody else caught this thing. Another has been Deep Impact's observation, and that was actually a comet hunter. And then another more recent one was the Chandrayaan mission. So this is one from India's space agency. So they found kind of differences in the hydration feature. When I say hydration, I mean something that is either H2O or OH. OH is hydroxyl. It can become water, but anytime we see one or the other, it's kind of hard to tell which one. But it does indicate that there's some kind of hydration going on, which is surprising for where it's found. So when Cassini passed, it basically observed hydration near the poles, as expected, but also in the highland area. So those were the brighter areas outside of the mare we saw before. And then Deep Impact observed basically across the lunar surface, it saw a lot of different hydration features, and usually across that many latitudes, it's very surprising. Lastly, the Chandrayaan-1 spacecraft, particularly the Moon Mineralogy Mapper, observed only at the poles, basically, a significant hydration. So there was kind of discrepancies going on between these three observations. They were surprised in the first place that we were seeing this much hydration. And so ground-based telescopes were then used to do really, really large, long-time campaigns, basically, to resolve this issue. So this is some previous work I did. We took data from the NASA Infrared Telescope Facility. We used the instrument called SPECS. It is the cross dispersion, that's the X spectrograph. And for those who are interested, the spectral range is about 0.7 to 3.2 microns. That is basically very close to visible. It's near infrared. And you can get very specific features in that range. So basically, the goal was to use this telescope to observe longitudinally across the moon, latitudinally with phase at the poles to see exactly where we are seeing hydration. And so that's SPECS there. And we broke up into teams, basically. So one team was observing up and down, basically, from poles across. But we were observing basically left to right through time. So each of these little data points, there's actually a couple there and here, they're at what were the subsolar points at that point in time. So the subsolar point is basically when the sun is pointed directly onto that part of the surface. It's kind of the version of noon for that part of the moon. So we were observing basically from phase to phase to phase throughout the month. And we wanted to take these observations and see if going across phase, which also means going across temperature, do we see this hydration feature? Do we not? Does it change, right? So we got together, different teams doing different things, and our team was looking at the subsolar point, looking for specifically what's called the 3-micron feature. So again, SPECS is from 0.7 to about 3.2-ish. And basically, we're looking at asteroid observations in this case, for example, where you can see a 3-micron band feature. So it's a little bit easier to see them in these cases. So this 121, I think Hermione, you can see it has like kind of a consistent spectrum, and then it dips really hard around 2.8-ish to 3 microns, and then it climbs back up. So you have some really sharp features. Other times you just kind of barely get a dip. So with 361 here, you see the spectrum kind of consistent, and then there's this tiny little dip there, and then it kind of goes back up. So we're still seeing about a 3-micron feature, but you can see sometimes there's less hydration, sometimes there's more. In the case of 10 Hygeia, the shape changes. So you go across these gray bands are where the atmosphere is and blocking out some of the light, basically. But we do see a drop going from regular spectra down to around 3 microns, but then it's this sharp check mark. And in other cases, 52 Europa, the asteroid, not the moon, it has this really curved, broad feature. So this hydration feature shows up in a lot of different ways on a lot of different bodies. So basically, our goal was to take our spectra of the moon and see if we could see any of these kinds of dips. So what we ended up doing was we took one of our best nights of data. This was in 2018, June 27th. And we split up 2 parts of that night's observations. So both spectra, unlike asteroid spectra, are kind of like a little more flat with a consistent curve across. These dotted circles here are basically where the atmosphere is opaque, so we don't get as much data there. And what we have to do to see if we can spot a 3-micron feature is thermally correct the spectra. So since the moon is hot, it's emitting a lot of radiation in a lot of different forms. So to see if there's any hydration there, we apply a thermal model of the spectra of the moon, basically. So the thermal model is applied to something like this relative blue curve, for example. And then it's subtracted off of the original data, and we get something like this. So this is the red dotted line, so we can actually see if there's hydration or not. As you can see, you don't really see much of a feature. Statistically, if you were to compare this whole area, you get the tiniest confirmation of some hydration. But what we found was basically in the subsolar region, there is little to no hydration. And later on, when all of our groups came back together, we found that there is a significant dependence of that hydration feature as you go across phase, across time, and across temperature. And so that was kind of the power of using a ground-based telescope and having these really, really long observing periods. But we can go even further than that. Going from ground-based telescopes out into lunar orbit, we have been able to observe fainter things and things that we usually can't see through our atmosphere. So once you get out of the atmosphere, you can observe a lot of different wavelengths. And that's what a lot of these different spacecraft do. So we have a lot of international Spacecraft. So we see some from Japan, some from China, the one from India, and they've sent many more. But in particular, we're going to focus on this one. This is LRO, the Lunar Reconnaissance Orbiter. This is one of the US's major lunar orbiters. It's been orbiting since about 2009 and continues to function with just about all of its instruments. And basically, we're going to use other forms of light to study fainter, harder to study parts of the moon with more time. So in particular, we're going to be looking at what we call the lunar exosphere. So the moon, unfortunately, does not have air for us to breathe when we get there. But it does have a lot of like plasma hanging out around it. So it's got things like helium and neon particles and argon that just kind of float around it. They come from things like the solar wind. It's a very dynamic environment. So all of the hydrogen and helium, that sort of thing coming in from the solar wind, run into the moon when the moon is exposed. And there are all of these processes that kind of kick up some of the dirt if they're energetic enough to bring things into orbit, to eject things out of orbit, to have things go onto the surface of the moon, so on and so forth. And so because it's a very, very thin layer of particles, it's not an atmosphere, so we call it an exosphere, it's so faint that we want to look into a different form of light to view it quite well in most of its species. So in that case, we look into the ultraviolet light regime. And to do that, we use the what we call the Lyman Alpha Mapping Project, or LAMP instrument. So it's an ultraviolet spectrograph that's on board the Lunar Reconnaissance Orbiter. Most of the time, it's pointed down in its orbit, just built for observing things like craters on the moon, ices on the moon, anything that's kind of hard to see in dark spots. But it also picks up a little bit of exosphere signal in the process. So we use very specific observation forms to measure these particles. So when LRO is passing in orbit over the moon, it passes the terminator where that light side and dark side meet, basically. And just as it passes into the night side, LRO is still for a little while out of the shadow of the moon. But it's pointed at the surface where the surface isn't really as bright. And so as long as the surface isn't that bright, it's a little bit easier to see some of that tiny exosphere signal. So what we end up doing is we take all these observations over time and we average them together, and eventually we try to constrain how much helium we're seeing, how much neon, how many whatever particles we're seeing over time. So this study was done before with LAMP data. Basically, about 27 different species were checked. And with decent error bars, they were able to constrain what species they were seeing in the lunar exosphere just kind of hanging out around the moon. But we have a lot more data since that study has come out. And so our goal is to basically reduce those error bars and better constrain that data and observe how it changes over time. The way that we do it is we take a spectrum of the moon. So unlike the asteroid spectra that we saw before, we kind of see this like weird, faint, low signal because we're in the ultraviolet now. It shoots up. This is an atmosphere. This is called Lyman alpha emission. This is a large hydrogen emission line that we're going to ignore because it's so bright. And then we get still a pretty low signal. So that's the overall spectra of us looking down onto the surface. But again, a lot of that light coming in from the surface is kind of overshadowing that exosphere signal. So we model it by basically figuring out what kind of reflection is coming in from the surface from things like ultraviolet bright stars. There's a lot of stuff in space called the interplanetary medium that's just like hanging out that we have to measure, and other things. And we basically scale it to the observation of choice by its time that we spend observing it. And that's this dotted red line here. So this is the model of the spectrum just from the surface, not from the exosphere. And we subtract that out, and we end up getting kind of this noisy but really rough baseline of what the exosphere signal is showing up as. We have to change this from case to case. Basically, from each orbit and each phase, the reflection is going to be different. I didn't do it on purpose, but we usually use the October 1st data set. And so we'll do it for things like almost full moon, new moon, and we'll change how the phase will have an effect on it. And so that model will change with each frame, and then we end up getting our sort of low, simple baseline spectra of the exosphere. And since it's noisy and we kind of need to see really, really fine detail lines, what we try to do is average many, many observations together. So the GIF on the left is us having these exosphere observations over the span of about 2 days. And so you can see they're all having this like little bit of noise. And then when we average them together properly, we end up getting this kind of really low baseline. And it looks like it's low signal, but that means the small, tiny peaks that we have are actual significant peaks. So our goal is to basically continuously do this over the span of years and improve upon this previous study. So far what we've gotten is we have a really clean baseline on the right. So there are species that we can constrain pretty well in this side. We are getting some extra leftover signal, which is telling us quite a bit about internal reflection in the detector. But one line that is very bright for us is similar to the previous study. Previously, they found helium very, very clearly, and it seems we have as well. So we'll be looking into how helium is changing over time, basically, in the exosphere soon. But yeah, thank you guys. Happy International Observe the Moon weekend, and connect however you connect.
Thank you, Patrice. Excellent talk. We're going to do the old switcheroo. Flip the slide. Thank you, Erica. Reminder, text your questions to that line. Don't be weird. Do you have a favorite moon feature?
I didn't show it, but Reiner Gamma, actually. It's actually a lunar swirl. It's not a crater, and it's like one of the weirdest features. It's magnetically charged for some reason, and no one's been able to figure out why. I think that's the only reason why I like it so much.
Highly recommend you look up pictures of the lunar swirls. Super weird. Do solar eclipses present opportunities for lunar science?
That is a good question. On the ground, they do. So similar to Danielle's talk, where we saw the coronagraphic effect, basically that can be very useful if you're using ground-based observations. In space, it's a little bit harder. The Lunar Reconnaissance Orbiter is on solar panels, and so to make sure that it is safe, we actually shut down during eclipses, even though that would be really, really good times to take data.
So with the moon being as bright as it is, does that limit ground-based observation or space-based observations in any kind of way?
Yes. In fact, most astronomers and actually many astrophysicists especially, the moon is really their enemy because the light just dominates the entire sky. And so if your galaxy is like only so many degrees away from the moon at its position at that time, you're not going to be able to observe. So there is that frustration. And even from space, even observing the moon itself, we do have to limit our view. Its reflection is so bright that our detector, our imaging part of our spectrograph can fry, basically, if we don't limit. So at the very beginning of mission, when the detector was really, really new, they shut out, I don't remember what percentage, but they shut out most of the light that was coming in until the detector was old enough and, you know.
You kind of touched on it in your talk, but so does solar wind affect hydration observations directly?
Yes, very much so. And in fact, that was found to be the major source of this variation in hydration. I said it was solar wind is a lot of hydrogen and helium, a lot of ionized hydrogen and helium. Ionized hydrogen is protons, so all of these protons are bombarding the lunar surface. So you've got the H part floating around, so you've got the hydrogen, and to make H2O or OH, you need the O. So as long as you've got oxidized minerals on the moon, which they are all over the place, those H's can stick to the O's, basically, and eventually make H2O or OH that is causing this absorption.
How low would a satellite need to orbit to make particle measurements of the exosphere?
That's a good question. So just from light, LRO orbits between, I think it's nominally about 50 kilometers above the surface. It's usually between 30 if we're getting really close, and then 80 is the farthest we'll go out. However, you can measure particles more directly with neutral mass spectrometers, ionized mass spectrometers, ion mass spectrometers, and I'm not sure actually what altitudes those are usually at. I don't know. That's a good question.
And would there be any value in having ground-based observations at the same time as space-based or even orbiting observations?
Yes.
Clears that one up. And then I have a science question because I study asteroids. Are are there any noticeable or notable rather differences between lunar thermal models and asteroid thermal models?
Yes. So as far as I understand, because asteroids have the complication of being sometimes rubble piles and that sort of thing, the thermal model that has to be built is more complicated versus the one of the moon. The colleague of ours that did the thermal modeling just used basic blackbody radiation, and that was basically the only thing that we needed. Yeah.
Good for them. That's so nice. Let's thank our speaker once again. Thank you, Patrice. Michael reminded me to mention there are some handouts on everybody's table. They are essentially descriptions of how LRO works and the science opportunities that LRO has, especially for eclipses. Those are for you to take if you would like, since we had talks circling around LRO, no pun intended.
We also have more if there's more than, if there's more demand than supply, we have the supply up here.
Yes. With that, thank you everybody for coming out. We hope to see you again next month. Everybody was slightly confused for a second. Do we clap? Do we not? And then I just stared at all of you to be like, yeah, we're going to clap. Yes, thank you everybody for coming out. We don't have the socials. However, if you would like to follow us, AOT.SATX, any kind of those variations of AOT SATX on Facebook, Instagram, Twitter. I think we're on Blue Sky or X, whatever. Yes. But if anybody would like to stick around for trivia, we will be having our monthly trivia round. See what Sam gave us this month. Max size groups of 4, please. No cell phones allowed. If you want to stick around for trivia, please raise your hand, and we're going to come by with the score sheet and a pen if you need it.
Oh, go ahead.
Did everybody who's playing trivia get a sheet? Reminder that we do groups of 4. So if you have more, split into 2 groups. But yeah, if without further ado, we will get ready to go in our trivia. Remember, please don't use your cell phones. We've got, what do you want?
Is the person who asked about in the room? Okay.
You left your lights on.
If they are, they ain't paying attention.
Yeah. So, yeah, we've got some great prizes for you all tonight. We've got the first and second place prize will win posters, really cool posters that are exoplanet related. And the third place prize will win a moon related prize, including some stickers and postcards. So we're very thematic tonight with the prizes. All right, who's ready for question 1?
Question 1. Saharan astronomy, bordering the Atlas Mountains and the Sahara Desert, the Medan, that observatory is located in which African country? Is it A, Egypt, B, Tunisia, C, Algeria, or D, Morocco? I asked already, but if you are, just for a quick little tidbit, on Friday, if you go to UTSA, because I think they're having First Friday, you go to the Flan building, you find the elevator, and you go up to the 4th floor. That's where they do all their observing. And then there's SCOBY, and you just go to SCOBY. But I don't know the others.
All right, and as a reminder, we'll come back to these questions if you need it. Question 2. Astrophenomena. This long exposure image taken in Uruguay in 2021 features what nighttime phenomenon? Is it A, a shooting star, B, stratospheric lightning, C, a string of pearls, or D, a speeding comet? Yeah, so this, if it is a comet and it is speeding, it's very unfortunate. It would get a ticket. And the fine would be 100 shekel?
Shekels?
I don't know what that is.
100 shekels?
Shekels? I don't know what that is.
100 shekels?
Shekels?
Shekels, I think, is Irish.
Oh,
Well, not anymore.
old Irish. Yeah, they use euros now. 100 euros. Yes, the fine. Yeah.
Well, this one's easier. Well, the obvious makes me concerned, but. All right. Question 3. Arabian celestials. The Arabic term al-Thuraya refers to which night sky asterism? A, the Big Dipper, B, the Pleiades cluster, C, Orion, D, Great Square of Pegasus, or E, Draco the Dragon. Hint, over the centuries, al-Thuraya has been adapted to a popular Middle Eastern name, Saraya.
Okay, question 4. Auroral zones. Churchill, Manitoba in Canada. I think there should be a comma there. It should be Churchill, the city of Churchill in the province of Manitoba. Whatever. Is located directly under the auroral oval and displays more northern light shows than any other city. How many nights each year are the northern lights visible here at Churchill, Manitoba? Is it A, 50, B, 100, C, 200, D, 250, and E, 300? And all of those choices are viable. Yep. Sam did not give you a, 400 days in a year type thing. He would. I know, that's why I'm shocked. Oh, wait, no, this one's you.
Question 5. Pacific Peninsulas. In this hit song by K-pop group BTS, the singers often express feeling left behind, cold, and allude to a failed relationship. The title of the song is the official asteroid number of the former planet Pluto. Yeah. Well,
All right. We're going to move on to question 6, the array of telescopes. Which of the... Aaron doesn't like stouts. Which of the following regions does not host one of the Event Horizon telescopes? Is it A, Greenland, B, Antarctica, C, Hawaii, D, France, or E, New Zealand? Which one does not have one of the Event Horizon telescopes? Bonus.
no. Oh. Does anybody need a question? Well, bonus first. Bonus first. All right. This goes in the bonus section because this is the bonus question. Originally named Nebecula Major and Nebecula Minor, which two celestial objects are now known by a different name? The new names were first adopted in official scientific writings by John Herschel in 1847. All right. Does anybody need a question repeated? Does anybody need a question repeated? 5? I got 5, I got 5, I got 5. Just 5?
Any other than 5?
Soon. Soon.
And if you are done, bring up your sheet and your writing utensil, please.
Please and thank you. We need the pens. Please. We are poor. Thank you. Oh, sorry. Thank you.
What were the answer choices for 6 again?
For 6, can you go down 1? Good. Thank you. Thank you, Ethan. Wait, go to the bonus slide. Thank you. All right. Is there, other than Blaze, are those all the answer sheets everyone's submitted? All right.
All right. First, we'll get to the answers soon, but first I need to see two teams: My Anus, No Uranus, and Pink Floyd's Moon Men. Please come up, or send a representative, or the whole team. I don't know. One representative from each team. All right. Thank you. And now I need to see one representative from three teams: Lunatics, Star Masters, and Marco. All right, let's go through some answers. Question 1.
Answers. Simply because this is a picture of Big Ben, and I've been there many times. That's Casa Grande. Moving on. Question 1. Morocco. Wait.
Morocco's in the north.
Like I said, I don't know where any of those is. Well, no. I knew the answer to this, but to my best knowledge, if I didn't know the answer, I would have thought below the Sahara would be better.
Okay, but it's not. It's above. All right. The second question, which was about the I knew it. I knew it.
I know.
Astrophenomena. It was a string of pearls. Yeah.
Does anybody know what that is? Anybody? Okay. What? No, are you thinking of the diamond ring? No, the beads. Oh, the beads. Okay.
What is it? Bailey's beads, right?
No, that's Bailey's beads.
Bailey's beads.
For the. Okay. The only explanation I can think of for this question is a SpaceX satellite train. That's the only thing I can think of. Why someone would call that a string of pearls?
Broken up as it comes through the atmosphere and you see it in pieces.
But in a long exposure, how would you know? Okay, this is samuel.hart@sweary.org. Please forward all complaints to samuel.hart@sweary.org or Samuel Hart. No, what is it? Samuel Hart Helio at Gmail. God damn, Sam.
Notice. I've noticed lately that the nights that he's here, the trivia's fine. When he's not here, all right. The Arabian Celestials. I knew it. It was the Pleiades cluster. Yes.
I don't think the hint helped whatsoever.
Huh?
I don't think the hint helped whatsoever.
No. Wait. Did the hint? Oh, okay. Did the hint help anybody besides Erica? Okay. Oh, wow. We were really off on that.
All right, question 4 was about the auroral zones. 300 nights. Okay. This has to be without cloud cover. It has to be without cloud cover, and I think an average between solar maximum and solar minimum. That's samuel.hart@sweary.org.
Wait, hold on. I don't know. Wait. This photo's in daylight, and you can clearly see aurora. No, that's the day. That's twilight. That's twilight. I mean, not day. Sorry, twilight, and you can still see green. So, yeah.
Twilight was in Washington.
Oh, shush. Yeah, who wants to go to Churchill, Manitoba with me? We can stop in Winnipeg along the way and catch a Jets game. Yeah. Pacific Peninsulas with question 5. The K-pop group BTS.
Behind the scenes.
Oh, no, the real question, what? No, I know. The real question was, what was the asteroid number of Pluto? And Aaron got this one right. It was A134340.
Is anybody a BTS fan that knew this answer just on BTS alone? Okay, because I was going to say 134340, like, I don't know, 3434. There could be, like, I don't know, something, but... there was something going on, but it had to be the lowest number because Pluto was like in the teens, I think, discovered. But I'm very surprised we got to the 100,000s by the teens. And then somehow we got out of order here. But I'm yeah. Question 6, where is there not a radio telescope? New Zealand. Basically, who doesn't have radio telescope capabilities in the microwave band?
And that's because Australia has all the radio telescopes down there. Yeah. Yeah. All right. The bonus, which Aaron and I can say it together, it is the Magellanic Clouds. Large and small Magellanic Clouds, which has anybody in this room seen them before? Just Lee. I knew you were going to raise your hand. I knew. I really want to see them. I've heard they're cool to see. It's worth a trip down to the southern hemisphere.
For me, the question was like, did John Herschel go to the southern hemisphere and see these things in the 1800s? I guess he did. Because otherwise it'd be like Andromeda and the Triangulum, but I don't think he established those names. Anyways, prizes. Well, it got complicated with the tie breaks.
Yeah. So, for those who weren't part of the tiebreaker, our tiebreaker question tonight was asking about the object that impacted the Earth to create the moon, the proto-Earth to create the moon. And the object's name was Theia. And the size of that object was roughly Mars size. So a Mars-sized object impacted the Earth, the proto-Earth, and then it spun a whole bunch of material around, and that became our current moon. So supposedly, but we're converging on that pretty hard now. So the third place prize, the tiebreaker actually didn't do anything, so we're just going to split the third place prize. It got rid of one. Sorry, Mark, you got eliminated. But the Lunatics and Star Masters, come on up, because you both got it all right, yeah. And so, yeah, they'll have, some of them will get some pretty postcards, and some of them will get some pretty stickers.
If you guys want to fist fight over who gets what, that is fair. You can go fist fight Sam if you want.
All right, and our second place prize, which will win this cool poster showing all the exoplanet missions by NASA in space and on the ground, and some NASA meatballs, Pink Floyd's Moon Man. Come on up. And then last, but certainly not least, with our first place prize of the night, winning this beautiful poster of PSO J318.5-22. Man, I just love exoplanet names.
Nothing like a Jet 2 holiday, huh?
Nothing beats it, but it is a directly imaged exoplanet in theme of Danielle. And the winner of our first place prize is my anus? No, Uranus. Congratulations. And what a team name. What a team name. All right. Let's bring the house down for the evening. We will see you all again on November 5th. We'll have two great speakers. Did we confirm Dinesh? No? Okay. Maybe newly minted Dr. Dinesh Radhakrishnan will be giving a talk. I hope so. We'll pressure him. But we'll let you know on the socials. Here they finally are. Here's the email list. If you're not on it yet, please sign up for it. And as always, thank you very much to Blue Star. We couldn't do it without them. Let's thank our wait staff tonight. Thank you so much. As you're checking out, tip them well. And of course, thank you to SWRI and UTSA for their continued support. And have a good night, everyone. Get home safe.